I don't know if that was because you knew I was forgetting or not, but thank you. Okay, there we go. So slope we talked about on Wednesday, and that was our y2 minus y1 over x2 minus x1. And remember, it doesn't matter which way you choose to be which point, as long as you're consistent with making sure that whichever y you put first, you put its corresponding x first. Personal preference, I always like putting the larger y value first, so I would have done 15 minus 2 over 4 minus 10. And here's where my arithmetic gets tested, 13 over negative 6. I don't remember what classes I've told so far, but guys, my arithmetic's terrible. So if I ever say that 2 plus 2 is 5, just, yell at me. So 13 over negative 6 can't be reduced at all. And just to clarify, of course, if done the other way, the negative would have been on the 13. Same exact number. Doesn't matter where the negative ended up. It's still negative 13 over 6. So that's that one. And of course, as always, if you've got questions, stop me in chat, or you can unmute yourself, whatever floats your boat. For the second one, again, personal preference, I would have put the 7 first. And so then negative 1 minus 3. So 7 minus 5 is 2. And negative 4. So that reduces to negative 1/2. And then the last one, 16 minus 8, personal preference, 2 minus 4. You would get 8 over negative 2. So 4. Why does that sound wrong to me? No, that's right. Okay, so negative 4 in either case. Alrighty. I'll wait 15 seconds to see if any questions pop up in chat, because I know typing questions can take a couple seconds. And we'll just dance.
There's a fire drill in East Quad right now, so there's some.
Yep, I've gotten multiple people let me know about it. It's fine. Of course, I record these so you can pick up the part that you missed, and you're okay. Sounds like a fun time. All right, so not seeing any questions, so we will move on to our. It doesn't matter. So with slope, it's usually written as y2 minus y1, but it's going to give you the same exact thing if you do y1 minus y2 and then x1 minus x2. These two are going to give you the exact same result. The negative just might be in a different spot, but it's technically the same number. So it doesn't matter which one you use for which. No problem. All righty. So now we will go back to notes. So now I gotta share, where's 1.2? There we go. And I gotta, yep. So at the end of class on Wednesday, we had talked about this interpretation question. So we had talked about how to find slope, and then we did this interpretation thing, excuse me. But we never really actually got around to doing much with slope. So now what we're gonna do is we need to find the actual equation of a linear line. We need to be able to actually find it. Now, one thing I want to note really quick, just a generic note, is that along the way, throughout my notes, I kind of take this a pause to do a process, and I just want to explain the reason I do this really quick. So when it comes to studying mathematics, I find that a lot of people can have a hard time trying to figure out how to study for math. And so a lot of people will often just do a bunch of problems until they're blue in the face. And I'm not saying that you shouldn't do problems to practice. That's the way you get good at math, is you practice questions. But specifically when you're trying to study, I think it's better to focus on the processes and making sure you have those down in your brain, as well as doing practice problems. But say, for instance, there's this weird phenomena where, you can do as many write an equation of a line questions until, your hand falls off, and then all of a sudden you're taking the exam and you completely blank. And you're like, I know I did a million of these, but I don't remember how. If you had studied and taken some time to make sure that you have the process in your brain and you kind of memorized it. I don't like the word memorize, but just to make sure you remember it, which I guess is memorizing, so I should stop getting on my soapbox about that. But if you remember, okay, well, if I want to find the linear equation of a line, okay, I got to find the slope, and then I got to put it in y equals mx plus b, then I got to solve for b. And if you can kind of like talk yourself through the steps, then you're better. So while yes, you should definitely do practice problems when you're studying mathematics, but also if there is kind of this set process, try to also take some time to look at those. So not everything has a nice process that can be written out in super nice steps, but whenever it can, I try to take the time to focus on it. So that's what this is for. So to write the equation of a line given 2 points, the first thing you're always going to do is you're going to find the slope between those 2 points, just like the warm-up. What you're going to do then is you're going to take this slope and you're going to choose 1 point, whichever one makes you happier. And my pen is freaking out. 1 point. Use in either slope-intercept form or point-slope form. So the slope-intercept form, to remind us, was the y equals mx plus b. And the point-slope was the longer looking one. Now, I'm pretty sure I mentioned this before, but if I didn't, just to reiterate, I don't mind which one you use one over the other. I find that most of the time people go for the y equals mx plus b, so that's usually the one I'm going to default to when I'm doing questions. But if you ever want to see the other way, just let me know. This first example we're going to do, I'm going to do both ways, just to start out the first example like that, and then most of the time I'm just going to default to the y equals mx plus b because I find that the large majority use that. But then your third, you're using slope-intercept form, what you're going to do is you're going to plug in the values y, m, and x, and you're going to solve for the remaining value of b. And then for some reason, people usually stop there and they forget that you then actually have to write the actual final answer. So if you're doing this way, make sure you actually find b and then use it to write the answer. The answer isn't just finding b, you then have to put it together. But if you're using point-slope form, you're going to plug in the values for your slope and your x naught and your y naught, depending on the point that you chose. And then you'll usually want to solve for y, so you'll usually want to swing this y naught over to the other side. Sorry, something keeps flashing on my laptop. I think everything's okay. So you usually want to swing that y naught over to the other side, and depending on who's asking, you might also need to distribute the m and do some algebra, so that way it can get a little more tedious. In terms of Wiley plus, I believe they usually prefer the mx plus b. I'm not 100% on that, but I'm pretty sure that it's usually expecting a mx plus b form. So just be aware of that if you are someone who likes to use point slope. So I will pause there for just a second. And then, so let's do an example. And there's a typo in this question that I didn't catch when I printed them. If you're keeping track of these notes yourself, there's an extra dot, extra period in this first one that should not be there. It should be 238.3. But, so, example. The solid waste generated each year in the cities of the U.S. is increasing. The solid waste generated in millions of tons was 238.3 in 2000 and 251.3 in 2006. Assuming the amount of solid waste generated in U.S. cities is a linear function of time, find a formula for this function by finding the equation of the line through these 2 points. And then once we have it, we're going to use it to predict the amount of solid waste generated in 2020. So the first thing we have to do is we actually have to do a little bit of work before we can even write the equation. So first off, we have to kind of figure out, well, first off, let's give ourselves some variables to work with. So I know we're used to x and y, but let's use variables here. I'm kind of going to base it off of what we're talking about. So we're talking about solid waste. So that's let's just use W for that, for waste. And then we're also using time, so let's go ahead and use t for that. So now we need to figure out which one of these variables is going to act like our x variable and which one's going to act like our y variable, because that's going to, change the way that our points are going to go. So that's when we need to kind of look for it telling us which is a function of the other. And here it gets a bit wordy, but it does say waste is a linear function of time. So if I just take out some of the extra words, so waste is a function of time. And so way back when I said, you want to get used to this kind of phrasing, but remember that it also kind of writes itself out. So waste is a function of time. So now we know that the t values are going to act like our x's and our w's are going to act like our y's. One last thing I want to do before we even get started with the actual problem is I want to let we're actually going to let t be, and this is lagging pretty bad. Okay, so t is going to be years, let me make that look like an actual y, years since 2000. This is going to be a very common occurrence with questions that we take years to be, whenever we have years as one of our variables, it's very likely that it's going to be years since something. And if you're the one who's choosing, it's pretty much going to start at the earliest year that you have in your data set. So since the data set starts in 2000, we're going to have t be years since 2000. Now, so again, Wiley is usually going to use that pattern. Say this was a question on an exam and you didn't do that and you just let your t values be 2000 and 2006, you would still be right. Your numbers would be way bigger, but you would still be right. Okay, so unless I specify that I want that to be in years since something, if it's a question written by me, you don't need to worry about it. But sometimes it's usually easier to just let that happen because it makes your numbers smaller. But be very careful with Wiley because they usually specify that it's years since something. Anyway, so now we can get around to actually answering the question. So I want to be able to look at these two pieces of data I have, and I have to pull out, what points am I actually working with to write this equation. So I have, t comma w. So let me write these two pieces of data in that format. Well, the first one's in 2000, but if we're using t as years since 2000, that's going to be 0, because 2000 is 0 years since 2000. And 238.3. And then my other set is going to be, so 2006 then becomes 6 years since 2000, and 251.3. So now that I've done all of that preliminary work to just get the 2 points that I'm going to use to write the equation of a line, I can now write the equation of the line. So I go back to that process that we just talked about. So the first thing you're always going to do is find your slope. Personal preference, I always put the larger y value first. And divide by 6 minus 0. I trust and believe we could type that into a calculator. It will come out to be 13 over 6, which is a little gross because it doesn't reduce, but, happens.
What I have to do is I have to go about finding the equation. Now, with this specific problem, there is kind of a way to, cheat is not the right word. What's the word I want? If I can't think of it in 2 seconds. I can't think of the right word, but there's kind of a way that you can kind of cheat to the end in this way. I don't want to say the word cheat, but I can't think of the word that I want to use. Shortcut. For this specific problem, there is kind of a shortcut where you can now just jump to the end, but not all questions have that shortcut. So I'm going to talk about the shortcut in a second, but I'm going to do the full process first. Okay. So the full process would then say that I have to choose which one of these points makes me happier. And while the one with 0 would make me happier, I'm going to go against my instinct and choose the one that has 6 in it. Because again, I'm trying to do the long process so that we can make sure we can do it
in the cases where we can't shortcut. So say that's my words are breaking, my English isn't working. Say that's the point I choose to do the rest of the problem with. So now I want to put it into my linear form. So W equals MT plus B, because different variables. So I've got 251.3 equals, that 3 got a little messy, but oh well. Our slope of 13 over 6 times 6 plus B. So this is obviously the y equals mx plus b way, and I'll show the point slope way in a second. So the nice thing is that those 6's are going to cancel each other out, and we're just going to get 13. And then to solve for b, you're going to subtract 13 from both sides. And then we've got one last thing, but Jake, what up?
How do you know that the first point is 0 as opposed to just like making the t-value 2000 as opposed to 0?
So I'm doing something that's very common and saying I don't like large numbers, so I'm going to let t be equal to years since 2000.
Okay.
So since I'm making that kind of declaration that that's what I'm using, 2000 is 0 years since 2000, so I can use 0. Again, if this was Wiley, that's most likely the way they're going to want you to do it, and they might even specify, they will usually specify that it's years since whatever. Say this was a question on the exam, and you just used 2000 and 2006, that's perfectly fine.
Gotcha.
It's just, personally, I like smaller numbers, so I like to take the usual convention of years since. Bleh. All right, so we found our b value, and I kind of noted before that a lot of times people just like to stop here and think they're done, but you're not. So once I have my b value, you then actually have to write out the actual equation. And the actual equation would then therefore be w equals our m value of 13 over 6 t plus 238.3. So now I want to talk about the two slightly different ways you could have done this one. This color is better. So say, before I do the point slope way, let me talk about the shortcut way. The nice thing about this one is that we were given the data point that's associated with t equals 0. So if you remember, in general, I'm going to erase this in a second, so I'm just going to write it right here. Y equals mx plus b. The b value is the y-intercept. Now the y-intercept means that x equals 0. So it's the point 0 whatever. So since we're actually already given the y-intercept, once you find your slope, you can kind of just jump to your answer, because note that the b value we did find is exactly 238.3. So if you're given that data point, the 0, whatever, you can jump right to the answer. You don't have to do this step in the middle. But there's a lot of examples where you're not given that data point, so that's not possible. Okay, so that was kind of the shortcut that you could have taken for this one. And then one more thing, because I said I would do both ways for this first example, and then other examples I'm just going to do one way. Say you wanted to do the point slope way. Maybe I should write that out instead of just saying PS way. Point slope. So then we would just be writing our equation as, so say I still chose the 251.3 as the point that I'm using, then it would be w minus 251.3 equals 13 over 6 t minus 6. If this were an exam for me, you could totally leave it like that. That's perfectly correct. The bad thing about point slope way is, especially usually with Wiley, they want it written like this. So if you do point slope way, you can still get to the final answer. Sorry, it's lagging a little bit. I gotta get used to that. So say you do the point slope way, but Wiley wants you to write it like this. You can still get there. You just have to do a bunch of algebra. You've got to distribute the 13 over 6 and then add the 251.3 to the other side. So this way definitely gets a bit more tedious if you need the answer to look like y equals mx plus b. But if you prefer that way, whatever floats your boat. But I find that most people usually use this. But again, whatever you like is fine. All of that was just for part A. We haven't even answered part B yet, but part B is a bit shorter. So part B asked us to use this formula to predict the amount of solid waste generated in the year 2020. So again, since I'm using T is in years since 2000, then I want to plug in 20. So I'm going to take my equation and plug in 20. And I've apparently scrolled over too far because we've lost the 0.3 in the above thing. Now I've gone too far that way. This doesn't like me today. Nope, I made it worse. Why does it hate me? You know what? That's good enough. I'm not going to touch it anymore. I trust and believe we could type that into a calculator. What this is going to give you is approximately 281.6. One last thing is that we should put the units on this guy. So we got to go back and find what the units of the solid waste were. So I'm going to reread the problem. So the solid waste generated, blah, blah, blah. The solid waste generated in millions of tons. So this would be millions of tons. Whew. All right. So that's that one. I will wait a couple seconds to see if anyone pops in with a question. Okay, moving on then. So say we weren't entirely sure if we had a linear data set or not. So the way we're going to be able to determine if a data set is linear is we're going to look at if the difference in y values is constant for equal differences in x. Okay. So let's look at a couple examples. Determine if the following data sets are linear. Now what we're technically looking for here is slopes. So you could take every pair of these points, find the slope between all of the pairs and compare them, but that sounds like a lot of work. So I'm going to try to do slightly less work to do the exact same thing. So what I'm going to do is I'm going to look at the difference between the x and the y values, kind of what that statement up there is saying. So I'm going to look at the difference between the x values. So from 0 to 1, I increase by 1. From 1 to 2, I increase by 1. And from 2 to 3, I increase by 1. So I've got these equal differences in x, so that's pretty good. And then I increase by 5, and by 5, by 5 each time for the y values. Now, this one is super easy to see because it was equal differences in x and equal differences in y. So like this statement up here it pretty much just flows straight out from looking at it. You've got equal differences in y. The differences in y is constant for these equal differences in x. But that's not always going to happen. These aren't always going to agree, but we're still going to be able to need to be able to figure out whether or not it's linear. So I want to go a tiny step further here. The thing we actually care about is the slopes. So to have a linear equation, you have to have a constant slope. But remember that slope is change in y over change in x. And these values here are changes in x's and changes in y's. So I could look at the slope by saying, okay, well, my change in y is 5 and my change in x is 1. And for the next set, it's 5 and 1. And for the next set, it's 5 and 1. So since all of these things agree, this is going to be linear. All of the slopes are the same. Slope is constant. Whereas if I look at this next one, and I look at my change in x's, I'm going to increase by 2, and then by 1, and then by 1. So you might say, okay, well, the changes in x's don't agree, but we don't necessarily care that they don't agree. We need the extra step. So let's keep going. Let's look at our change in y's. So this increases by 10, increases by 5, increases by 5. So these last couple sets look like they're going to agree, but does it agree with the 10 and the 2? Well, again, we're looking at change in y over change in x. So in this first set here, I'm going to have 10 over 2. Well, is that equal to 5 over 1? Well, yeah, they're both reduced to 5. So since both of those ratios of the change in y to change in x both equal 5, this is also linear. So it doesn't matter that these numbers don't necessarily match. What we care about being constant, what we care about matching, is the actual ratio of the change in y to change in x. So in this last one, and I'll wait a couple seconds to let that sink in. So in this last one, we look at our change in x's. We've got an increase in 10, an increase in 10, and an increase in 10. And if I look at my change in y's, we've got the first one decreases by 0.4. The second set decreases by 0.2, so if you kind of realize what we care about, you kind of realize that we can already be done, but let's just take the last data set. And then from 1.8 to 1.6, I go down by 0.2 again. Well, if I'm just doing this out in fullness, well, then we would have to say, well, is negative 0.4 over 10, is that equal to negative 0.2 over 10? Now, I forgot to put these both in a calculator to find the actual numbers, but since the denominators are the same and the numerators aren't, we can kind of already say that no, those are not going to be the same number. Okay? This is not linear. Slope is not constant. Because we just found that the slope between the first 2 points, being whatever the heck that actual number is not going to be equal to the slope of the last sets of points. So hopefully that makes sense. Let me know. I will wait a couple seconds to see if there's questions. And see if my brain decides to sneeze or not. No? Okay. All right. Oh, yeah, I thought we were done. But yeah, this last example. Right. So the following data is linear. So great, we're already told it is. We don't have to check it. Write the equation for p as a function of q, and then a function for q as a function of p. I wrote that kind of weird. State units for the slope in each case. Okay, cool. So I've got to do two things. So let me break on my screen so I don't run out of space. So the first thing I'm asked for is p as a function of q. P as a function of q. Told you had to get used to this phrasing. So again, it kind of writes itself out. So p is a function of q. All that to say, we wanted to try to determine which ones are acting as our x's and which ones are acting as our y's. That's kind of the first thing you always need to establish. So we know that our q's are our x's and our p's are our y's. I always bring it back to x's and y's just because I feel like people are most used to working with x's and y's. That's why I always do that. But anyway, so to write the equation of a line, we only need 2 points. So I'm just going to pull 2 of these 4 points. I'm just going to pick the first 2 because they make me happier. So now to make sure that I'm doing it in the right order, let me rewrite those 2 data sets in terms of the correct format. So our q's are acting as our x variable, so our 2 data points would turn into 100, 5 and 90, 10. So now that I have the 2 data points in kind of their correct order, if you will, I can go ahead and find the equation of the line. So the first thing you've always got to do is find the slope. So 10 minus 5, 90 minus 100. So 5 over negative 10, which reduces to negative 1/2. It's almost always better to reduce if you can. Again, for Wiley is usually a bigger stickler than I am. If you don't reduce, for me, it's not the end of the world. I care more about the actual process of finding the equation as opposed to whether or not you simplified. But anyway, so I'm going to simplify to 1/2. And then I have to pick one of these 2 equations. Sorry, one of these 2 points. I'm going to say 105 makes me happier. So I'm going to choose that one. And now, again, this is where I'm just going to start using the y equals mx plus b way, because I think most people are more comfortable with that. If you want me to show a different way, totally just let me know. And this time we can't shortcut it. We have to do it the long way. So I've got to put it into my y equals mx plus b form. So I've got 5 equals negative 1/2 times 100 plus b. So 5 equals negative 50 plus b. Add 50 to both sides. B equals 55. And then again, for some reason, a lot of people like to stop there and think they're done. You're not. You got to write the actual answer. So now, usually y equals mx plus b, but here it's going to be p equals m cubed plus b, just to be clear. So the equation is going to look like p equals negative 1/2 q plus 55. And then the other thing we were asked for in each one of these cases is for the units of the slope. So let me go back to the slope really quick. Well, it's not too bad to kind of walk yourself through the units of the slope, because the slope is a y value over an x value, right? A change in y over a change in x. So the units are just whatever the units of y are over the units of x. So the 10 and the 5 were dollars, and the 90 and the 100 were tons. So this is going to be dollars per ton for our units.
Wait, where'd you get the negative 1/2 from?
So that was my slope. So my 2 points I was working with was the 100 and the 5. 105, 90, 10, and that came from my table right here. And then I found the slope between the 2 points, so I subtracted the y values and then subtracted their x values, got 5 over negative 10, which reduces to negative 1/2. Is that okay, or do I need to go into more detail?
No, you're good. I was just looking at it.
Okay. Yeah, I kind of did the rest of the problem and then went back to it, so that might have been confusing too. So, give a couple more seconds if anybody else has another question. Cool. So now we're asked to do essentially the opposite way. So now we're also asked for q as a function of p. So q is a function of p. So essentially now our variables are kind of flip-flopped. So if I use those same 2 points, the 5, 100, 10, 90 data set, let me write it in terms of how this is going to go now. So our p-values go first, so it would be 5, 100 and 10, 90. So we kind of got to keep track of which one's acting as what. And so now that now that I have my 2 points, find the equation of a line, I always start with the slope. So personal preference, larger y value goes first, but whatever floats your boat. So 100 minus 90 gives us 10, 5 minus 10, negative 5, which will reduce to negative 2. Okay, cool. So we've got our slope of negative 2, and actually while I'm talking about my slope, why don't I just finish the units here now? So the 100 and the 90 were tons, the 5 and the 10 were dollars, so this would be tons per dollar. And just for the sake of being, I don't know the word, I'm going to choose the point 1090 this time around as the point that I'm going to use to finish it. Come on, go away. Thank you. So now I've got to put it into the y equals mx plus b form. So I've got 90 equals negative 2 times 10 plus b. So my pen has decided to stop working real quick. Here we go. B disappeared. Okay, so 90 equals negative 20 plus b. Add 20 to both sides. 110 equals b. Again, you're not done. So now we have q equals blah, blah, blah. So q equals m, so negative 2, p plus 110. And now we're done with that question. Any questions on that example? Alrighty. last definition in this case, formulas of the form y equals mx plus b represent the family of linear functions where m and b are called the parameters. Out of this definition, the parameters is a bit more important. So if you see a question Wiley that talks about parameters, it's just talking about the m and the b values. And that's the end of 1.2. So I know we're kind of close to ending, but I do want to start 1.3 because I also have to say something about your homework about it because 1.3 is on your homework. But I'll talk about that at the very end. So I'll give a couple more seconds for people to get this down before I switch to 1.3. And again, I'm sorry, the 1.3 came up like right before class on Wiley, Blackboard, because I thought they were up there and then they weren't. So that was my bad. Alrighty, so I've got to stop sharing and then, come on. I've got to actually pull up 1.3 that I don't have up yet. So, boink, and then I have to reshare my screen. Boink. Alrighty, average rate of change. So, if y is a function of x, so y equals f of x, of course, then the average rate of change, whoa, the average rate of change between a and b is going to be the following. Now take note that that looks very suspiciously like slope. And it's because it kind of is. And the difference is slightly hard to explain. I have a picture coming in a second that will hopefully make it a bit more clear. But essentially, slope is used specifically when we're talking about a straight line. And average rate of change is a slope. But the reason that we have a different name for it is that it's used in much larger and much broader contexts than slope is. So we can talk about the average rate of change between two values on a function that's not a straight line. Whereas when we're talking about slope, we're specifically talking about, oh, a straight line, the slope of that line is blah, blah, blah. Whereas the average rate of change is used in much broader contexts. But when it comes to, remembering how to do the average rate of change, if it helps you, you can think the average rate of change is a slope. So you just have to find the slope. So if it helps you to kind of link the two together, because they are linked, so if you want to think about the average rate of change as being a slope, especially when it comes to calculating it, that's a perfectly acceptable way to think about it. So let's say I have this table here that's got men's winning pole vaults related to the Olympic year. So say I want to find some average rates of change. And maybe I'll just leave that up there. So say I want to find the average rate of change between 1960 and 1964. So the first thing I'm going to do is I'm going to go find those two data points from 1960 and 1964. And then if these are my x's and these are my y's, which if it's not specified in the problem, you can assume the first thing in the table is the x and the second thing is the y. If it's not specified, you get to kind of just assume that that's the way it is. So if I want to find the average rate of change, well, that's just going to essentially be the slope between these two data points. So I'm going to have 510 minus 470 over 1964 minus 1960. Whoops. So that's going to reduce to 40 over 4, which reduces to 10. What up, Aiden?
Yeah, I missed the name of the section. Sorry. Got it. Thank you.
Okay. So that would reduce to 10. And if I wanted to keep track of the units, so again, these top units, the 510 and the 470, were centimeters. And the 1964 and 1960 are, of course, years. So this is going to be in centimeters per year. And then say I wanted to find, well, what about the average rate of change between 2008 and 2012? Well, let me go find those data points from 2008 to 2012 and find the slope between them. So 597 minus 596, 2012 minus 2008. That's going to reduce to 1/4. We haven't changed what we were really calculating yet. That was phrased badly. The units are the same. So this is still 1/4 centimeter per year. And then, okay, well, what about 1960 to 2012? We pull those two data points. If I pull those two data points, I'm just going to find the slope between them. So 597 minus 470, 2012 minus 1960. It's going to reduce to a really gross number, 127 over 52. Again, our units haven't changed, so that would be 127 over 52. If you wanted to write it as a decimal, that's approximately 2.44, but whatever floats your boat, centimeters per year. And that's the basic idea of average rate of change, is just essentially the slope between those 2 points. Now, because we are running out of time, and again, because 1.3 is on your homework, and I'm going to talk about that a bit more once I go through this last thing I want to talk about, I'm going to skip through to, so I'm going to skip these next two examples. We're going to come back to them on Monday. But I want to skip forward a tiny bit, talk about one tiny bit more bit of it that was in English. And then I'll ramble about your homework, and then I'll let you go. So the average rate of change does not imply that the change is constant over that time interval. So say you were traveling from Columbia to Charleston. It's about 104 miles, and say you do it in 2 hours. Your average speed would then be 52 miles per hour. If you just think about it in terms of, logical driving, you obviously weren't driving 52 miles the entire time. Sometimes you would have had to been driving slower than that. So then obviously there should have been times faster than that too. What it's saying is that over that whole entire time interval, on average, your speed was 52 miles per hour. So it's not telling you exactly what's happening in that time frame, but it's telling you on average what's happening. So essentially, and here's kind of why slope and average rate of change are kind of the same thing, but used in different contexts. I have this function here. It's not a straight line. It's got a little curve to it. But say I wanted to talk about the average rate of change between A and C. Well, that function isn't a straight line, so I can't find the slope of that function. But if I wanted to find the average rate of change between A and C, essentially what that's doing is it's taking the line, the very badly drawn line, between those 2 points. And what's going to happen is the average rate of change, which I'm going to abbreviate because I'm lazy, between A and C is the slope of the line between them. So that's what I was kind of trying to say, is that average rate of change is technically a slope, but it's kind of like slope is used in the very strict category of straight lines, an average rate of change can be for anything. So you can find the average rate of change for anything, even though the average rate of change is talking about the slope of a line. Hopefully that makes a little bit of sense. So while the average rate of change is a slope, it's used in a much larger, broader aspect than just talking about the slope of a line, if that makes any sense. The last tiny little thing I gotta say is something just about verbiage in case you see it on your homework. We can also consider the idea of the average rate of change in terms of a distance function. So if we were talking about a distance function, so distance equals a function of time, so given a time it tells you the distance, then if we were to calculate the average rate of change for distance, and maybe I'll say distance function, that would be some change in distance over some change in time. And the verbiage that you need to be aware of is that this is sometimes called average velocity. So if you see average velocity on your homework, it's not something new, it's just
Change in that very specific
context of a distance function. And now I've got 1 minute, probably barely a minute, to ramble about your homework really quick. So technically your homework covers 1.3. And usually I try very, very hard to make sure everything that's on your homework is covered by Friday. And we were supposed to get through this whole section by today, but things didn't work out the way they should have. We're a little bit behind, so that didn't work out. So technically, there is a small amount of your homework that we haven't talked about yet. Now, your homework's due on Monday at 11:59 p.m., so technically it's after class, so we still have Monday to talk about material. So while it's not ideal, I'm going to leave it as such for now because it's such a small subset. Like if we hadn't even been able to start 1.3, and I know we didn't get too far, but average rate of change, it's really the bulk of it is average rate of change, and you're just finding slope. So I'm hoping that it's not the end of the world. But going forward, I try very hard to have your homework material end on what we cover on Fridays, but this one, it didn't quite work out. So sorry about that. Someone in the other class asked if then I could post the full section 1.3 notes on Blackboard. You know, if you wanted to try to look it over yourself, I will do that if anyone wants to try it, but it's really not going to be that much more on Monday that you're going to have to finish if you like complete everything that you can up to, you know, what we haven't covered yet. So I just wanted to make you aware of that. I don't think there's anything else I needed to officially say, so have a great weekend. I will see you on Monday. If you have any questions, I'll be around for a couple more minutes. So you are free to ask them if you have them. Otherwise, goodbye.
Thank you.
You're welcome. Bye. Have a good day.